Hi, my name is Kimm, and I'm presenting eAudit, a fast, scalable, and deployable audit data collection system. This work comes from the Secure Systems Lab at Stony Brook University. Our lab is focused on the investigation of advanced persistent threats, which are attack campaigns characterized by their ability to get past preventative measures on enterprise systems and their ability to remain active yet undetected for weeks or months at a time. Because of this, we need to rely on after-the-fact detection and performing forensic analysis in order to understand an APT's impact. The best source of data in order to conduct effective APT detection are audit logs. And we know that over the past several years, all the major APT investigation systems rely on syscall logs. So we consider system call logs the gold standard in this regard. They also provide full provenance to connect all pieces of an attack campaign. What are the drawbacks of existing audit data collection systems? Well, the first is that they produce high overhead. For example, let's consider the widely used Linux Audit D logger system. Our experiments show that it slows down workloads eightfold, and that high overhead indicates that these logging systems are unable to keep up with excessive system call rates, and thus they drop records. The second drawback is that these loggers produce large data volume on hosts. These two weaknesses enable powerful attacks against logger systems. The first attack a intruder can conduct is by forcing data loss by generating intense amounts of benign activity. For example, they can conduct a denial of service attack. And as a result, an attacker's activity can be obscured by the loss of data and the high proportion of benign events. The second is they can actually uh, exploit the log tampering vulnerability. And this is characterized by a window, which refers to the amount of records that remain in the logger's memory at any given point. If the attacker gains root access, they could erase audit records before they're able to be transmitted to a secure server. And as a result, the attacker can remove evidence of privilege escalation. So let's actually take a look at the data loss on existing auditing systems. And we see here a measurement of various commercial and experimental audit logger systems. We actually use a workload called Postmark, which is a widely used file system benchmark, to test their ability to capture data. And we can see that existing auditing systems drop a majority of events even at moderate loads, and that more intense loads will produce over 90% data loss, which means that these systems capture essentially nothing. Let's take a look at the log tamper window on these existing systems. So we see that these systems can produce log tamper windows of sizes ranging from 50 to 500,000 audit records. And so if the logger is killed, this is more than enough to potentially wipe out all indications of a break-in. So it's clear that audit loggers aren't able to fulfill their primary goal of preserving records for post-attack detection. So this motivates us to develop a new audit collection system that's resilient to both data loss and log tampering attacks. But what are the challenges in building this new system? Well, the first is that it's difficult to develop, debug, and maintain kernel code. And second, we need to design a system that's able to handle the high rate of system calls, which can reach up to tens of millions of calls per second. This is where eBPF comes into the picture. eBPF is a virtual machine implemented in the Linux kernel, and it allows for the compilation and loading of safe kernel extensions, which means that we no longer need to make changes to the kernel source code. This also makes it well suited for system call logging, as we can intercept every system call entry and exit. Even though eBPF only allows for read-only access to the kernel, This is sufficient for our purposes for logging. So let's discuss a straightforward system architecture we can design around eBPF, and we call it eAudit. So we can have a module that captures system call arguments from the Linux kernel and then sends these records directly to the user level. And then a user level process will then write these events to file. Let's then discuss a base naive design around eAudit, and then we'll discuss 3 optimizations we can use to improve its performance. So with this, we'll capture about 80 provenance-related syscalls. We'll intercept each syscall, immediately send it to the user level, and then write to disk. And then let's also make the record sizes for these calls comparable to that of previous systems, say about 200 bytes. What we see is a substantial improvement in data loss. For example, the previous loggers were experiencing about 60% or up data loss for postmark, while our system produces less than 20% data loss. However, more intense load will push these data losses to very high levels. Our results showed that eBPF alone can't solve our data loss problem. And so we introduced our first optimization, which is a compact encoding scheme, in which we log just a system call and its arguments. And as a result, we're able to reduce the eAudit average record size from about 170 plus bytes to about 17 bytes. And as a result, we're able to reduce data loss from about 10 to 20% across most of our benchmarks. So the record size does help, but it seems that the primary issue is not the size of the records, but the number of entries that are being enqueued on the ring buffer. We found that needing to access the ring buffer on every system call is causing substantial data loss. We know that the ring buffer is capable of transmitting large volumes of data, but the rate of messages increases contention on it. So our solution is to use a per CPU cache, in which each cache will hold messages of size p, where p is defined as the number of system call events. And when these caches fill up, they are then flushed and then written entirely to the ring buffer, which thus reduces our system call rate by a factor of p. By using these message caches, we're able to experience a dramatic effect in overhead, reducing it from up to 100% down to the single digits. For example, if we set p to 100, we're able to get overhead to dip below 5% for all benchmarks. And for our experimentation, we use this p-value. And as a result of using a high enough p-value, we can actually solve our data loss problem. Let's go back to addressing the log tempering vulnerability. Larger values of p mean that we increase the throughput of our logging system, but in turn, this also means that we increase the number of records that are buffered in our per CPU caches, and we refer to this as latency. So how do we find the right balance between having low overhead while also maintaining small log tampering windows? Our final optimization is a performance model for balancing both overhead and latency. And the 2 parameters responsible for this are P and W. P, which is the message cache size in terms of the number of system call events, and then W, which is an interval of how often the user level is woken up to receive messages from the ring buffer. And so what we're trying to do is find an optimal trade-off between latency and overhead by tuning P and W. This is our full performance model, and I want you to draw your attention to the metrics, specifically O representing overhead and L representing latency. And then next, our optimization goal. So our goal is to minimize the product of O and L. And what we can do is we can differentiate O times L with respect to W and setting equal to 0. And if we solve, we're able to derive a formula that can give us an optimal value for W. Next, we perform an experimental validation of our performance model. Our goal is to see how well our model matches the actual measurements on our experimental platforms. The x-axis represents our measured overhead, while the y-axis represents overhead predicted by our model. And the diagonal line indicates that the measured overhead perfectly matches that of the predicted model. And you can see that the data points fall well around this line. This chart shows a direct illustration of achieving an optimal value for W. The curves in this chart represent W's effect on overhead and latency. For example, let's take a look at latency at around 200 events. We can see that small values of W will yield relatively high overhead. By increasing W, we start to approach a minimal overhead measurement. Using our theoretical model, we find that an optimal W is about 5 to 8, and our validation supports this. In summary, we're able to eliminate data loss, and our compact encoding scheme lets us produce 10 times smaller event records compared to previous works, thus substantially reducing our data volume. If we were to combine all three of our optimizations we introduced earlier, we achieve a decrease in overhead by a factor of 18 times compared to our unoptimized design. And what does our actual overhead look like? Well, it's 3% across all benchmarks and benchmark loads. Finally, let's take a look at our log tampering window results. We compare our windows to that of the next best performing system, Sysdig. We maintain a small log tampering window that is hundreds of factors smaller than that of Sysdig's. On average, eAudit produces tampering windows of a couple hundred records, while Sysdig produces records ranging between 35 to 200,000 records. Even at a max benchmark load, our system will only generate an average size window of about 1,000 records. In summary, we accomplished the following. We identified the major bottlenecks in existing audit collection systems: high overhead, data loss, and log tampering vulnerability. We also presented several new techniques to overcome these challenges: our compact encoding scheme, two-level buffering design, and an analytical model to optimally tune latency and throughput. But don't just take our word for it. We want you to try our system for yourself. So go to www.eprov.org, where all of our source code and measurement scripts are available. Thank you.